So we stay in the Mediterranean, but go now to the Western Mediterranean, which is quite different. Already, I don't have the map here, but if you look the heat flow, while the Eastern is very cold, the Western is very warm. So we were lucky the last 7 years to have a few cruises for new marine heat flow data acquisition, the Western Mediterranean, with our small heat flow group at the Sorbonne University and the ESTEP laboratory. So there is also Frédérique Rolandone, who is also here, who is in our group. And I want to mention two students, Massimo and Simon. He already defended, but Simon is his defense is in 2 weeks, so he's stressing now for his defense. Okay. I want to, well, I will try to convince you that seafloor hydrothermal circulation can also occur on the continental margin. So I start with this because as Dave showed us, I think it was in the late 70s or begin 80s that the first black smokers were discovered, and so that this community quickly interpreted it as a convection of seawater infiltrating along the faults of the mid-oceanic ridges, and then taking all these elements and coming out again. So, but for a long time, the oceanic community stayed on this, on the mid-oceanic ridges, and focused on this. But in the meantime, in fact, the heat flow community already pointed out this heat flow deficit. So, as Dave showed us, the difference between the theoretical conductive heat flow that we should expect and the measurements from the cooling models and the measurements. And very quickly, this community suggested that it's probably related to some circulation. But it took still a long time and a lot of efforts. I think it's rather in the beginning of the 90s and to the 2000 that good proof came from different examples that this system of access, just on the flanks of the ridges, is active and proof of how the system was working. So now we know rather well that we have the infiltration of seawater in certain seamounts, basaltic seamounts, which is then transported over relatively large distances of several tens of meters, heating up, of course, and then discharging at other seamounts. And that this was discovered mainly by the seafloor heat flow, of course also with some geochemical tracers. Dave already pointed out the importance of this circulation on a global scale for element exchange and all this. I also want to point out that 1/4 of the global heat loss is in fact not measured or is lost by advection by this system, and is just not measured by our conductive measurements in the seafloor. So there are different criteria needed to have this circulation, but one of the most important is to have this access of some permeable conduits, so which in this case are these basaltic seamounts. So one question we could ask, why should this be limited to 65 million years in the ocean? Because we know there are seamounts also on older age of oceanic crust. So Lucasot showed in one of his papers that indeed if he used a good correlation between some local topography or ruggedness and this heat flow deficit in specific areas where we had good data, and showed that there was a good correlation. And so in the end he tried to show that indeed up to 170 million years crust we can, and we probably have also hydrothermal circulation. I should mention that von Herzen already pointed out in one of his papers, he took some case studies also of published data and showed that it probably indicates also that there was circulation already on, I think it was 168 million age crust. So we know, we are pretty sure now that it also exists. Of course, it's probably less intense than in the younger, because we have less outcropping than in the younger crust. So my idea was to go a step further and say why we would not have it on the continental margin, where we also could have the good conditions, where we could have some permeable layers and we could have outcropping. So I want to bring you to this area, which is the South Balearic margin, where you see you have a lot of seamounts, which before we went there, they were only described morphologically, so they were recognized, I think, already on multi-beam data, but they were not, well, they were never analyzed, so we didn't really know. There was one seamount, almost 150 kilometers along the same slope, this is the Émile Baudot slope, which was dragged, where one sample was dragged and which was proven to be of basaltic origin. So this South Balearic margin is located in the Western Mediterranean, which is considered to be a back-arc basin formed in the late Oligocene, early Miocene. So most of the deep basin is considered to be floored by oceanic crusts, even if there are not very good magnetic anomalies, because there is a thick sedimentary layer on top of it. And there is also in the sedimentary layer a thick salt layer, so which prevents to have good imaging the basement. Of course, on the margins, the thickness is much less, and sometimes there is no sediments. And we will see this is the place where we did several of our measurements. So the first cruises that we did, we succeeded to collect around 170 new data points around the Western Mediterranean. So we came up with this simple interpolated map, which allowed to describe a little bit better the regional characteristics, but also pointed out the existence of several local anomalies in the deep basin and in the margin. So in the deep basin, we could see that it was correlated mostly with diaperic structures. But on the margin, where we don't have any salt anymore, this was not the case. And so we were lucky to be able to go back to one of these anomalies on the margin and get a little bit more data to understand them. So we used the Atalante vessel, which is from the French fleet, scientific fleet. So we could have 56 new heat flow stations. So we used two instruments. So this is a heat flow instrument which allows to measure temperature and conductivity in situ. So it's not a Lister probe, as you see. It's the alternative configuration with the outrigger things. So which we have 7 on the 5 meter length. We have 7 outrigger probes. So it's with the Lister probe, the advantage is that you can have much more measurements. But the configuration is working well, and so we also use it in the POGO mode, of course, to have more data in a short time. So the cruise was like 10 days or less than 10 days. But in some stations we decided to use the core and to equip the core with these automatic temperature loggers. And in that case, of course, the conductivity we measured in the lab on the ship. And to comment on the question that Ilmo gave, we did some repeated stations with both of them. Heat flow in general is very similar, almost the same, and also the conductivity between the in situ and the onboard measurements are not very different. Of course, there can be some deformations in the core. So you have to control what's happening in your core. You open it afterwards, so you can check. The advantage is, of course, that you can do much more conductivity measurements than you can do in situ. So there are some advantages also in this, to do the measurements on the cores. But in general, I believe that they are quite good representative for the in situ conductivities. So I will show two profiles. One is perpendicular to the margin. Here, so here you have Ibiza, this is Mallorca island, so this profile is located here. So the red ones are the sediment corrected values, and you see that here where we have where people believe, because the OCT is not well defined, so some people put it here, other people here, but at least where ocean domain is rather well defined, we have a heat flow which is around 100. milliwatts per square meter. But then when we approach the OCT and when we go into the continental margin, you see that we start to have different anomalies. First, in general, an increase, but we also have this relatively low heat flow anomalies. Some part could be related to some refraction effects, but not all of this deformation. So another profile is then a long strike, exactly on one of these spots where we have this very low heat flow. And here you see that where we have normally a heat flow around 60, 65, you see that along this very detailed transect of around 30 kilometers, we have a decrease slowly up to 0 milliwatts per square meter, and then increase again to the normal value, and then a really two very high values here, but well, they are not on this exactly on this profile. So you see already that we were very near to this, what is called the Los Martinez seamount. So here is a plan view of the same data. So the profile I showed you was this profile up to here. Okay. So you can see this is this Los Martinez seamount. When we look to a correlation of a cross plot of the thickness of the sediments and the heat flow, we can see some trends that gives us some indication also that hydrothermal circulation is active there. But this, of course, no real evidence. But what is interesting is, so we could. It's very difficult for us to explain this very large low heat flow zone differently than by a kind of infiltration nearby or in that area of seawater. So then we have two zones where we have heat flow up to 165 milliwatts. So it stands out to the regional ones. So the question is there a relation between these low heat flow zones and the high heat flow zones? So we dredged this structure. So this is what we got up, not a lot. And like usual, it's quite risky operation sometimes. We almost lost it because we passed a little bit the limit of the dynamo maximum that we were allowed. But in the end we got it, and well, I will not pronounce this mineral, but the petrologist told us that this is a product which is a common weathering product of underwater basalts. So we believe that it's a proof that, like in the Émile-Bedeau seamount, which is 150 kilometers away, that here also this is a basaltic seamount. So we couldn't do any age estimates because it was too altered. But in the Émile-Bedeau, they estimated something between Pliocene age of the basalt. So then I asked one of the students to look on the seismic profiles and to map a little bit where he believed that the volcanic substratum was extending. So the darker or purple is outcropping volcanic edifices, and then the lighter one is under the sediments. You can see so that a large part of this area has what we believe a basaltic substratum. So this is a cross section which is like here a little bit. So you see these two sedimented seamounts and then the one going out. So we also have several faults here. They are mostly along strike in this area, so which could be potential conduits for the circulation. Okay, want to do a little step aside because in the seafloor there are other processes of seafloor circulation that can drive seafloor sedimentation. If we are closer to the coast, we have our topographic driven flow from the continent that often goes several tens of meters under the offshore, and which can be accompanied by some seawater recirculation, so infiltration and that is resulting from this topographic driven flow. But we are more or less here, so we are like 120 kilometers from the shore, so I don't believe that we could have at this time an effect of this system. We are here, but we are much deeper. We are 1,500 meter deep, our low heat flow anomaly. So, and then we also have a steep slope, and then we have the D basin, which is around 2,800 meters. But what we expect if we have such a strong morphology in the deep sea floor, we expect this kind of course you need a certain permeability to allow it, but we expect this kind of haute convection, which is simply the result of the fact that the isotherms here are not horizontal anymore. So we get some lateral gradients that are sufficient in some conditions to create the upflow of fluids in the margins. On the other hand, so this is difficult to explain our low heat flow anomaly. I mean, we would expect rather to find some elevated anomalies on our study area here. On the other hand, as people who worked first on dolomitization, and then also in the Bahamas carbonate platform, they showed in fact that you can also have a reversed circulation that can reverse in fact this normal geothermal circulation and create circulation from the top here of a platform to deeper places. And in this case, it's induced by some residual brines that are generated by seawater evaporation here. So this model was developed for the Bahamas platform, where they have some quite good indications from boreholes with almost near zero gradient information. So they have quite good proof that this system exists. Of course, and some modeling studies by Jones and also by other people showed that it can create circulations over large lateral distances and also persist over large times. So this is quite interesting because at the moment, we are not on a carbonate platform, so we are at 1,500 meters depth. So of course, we don't have any evaporation at the moment in our study area. But if people in the Mediterranean know, of course, that we have the Messinian salinity crisis. So like 6 million years ago, we had an enormous drop of the sea level in the Mediterranean of around 1,500 meters. Well, there are different models, but most people go to this model. So this created also the large deposits of sometimes 1 kilometer of evaporites and salt in the deep basin, but also in the marginal basins we have sometimes in different places deposits of evaporites. This only lasted for like 500,000 years, 600,000 years, and then again the level increased to the present level. But this is a relatively long time, and during this sea level drop, some circulations could maybe have been set on could have been started and still persists at this time. So this is a kind of cartoon I made. So it goes from the Messinian here up to the present on the top, just to show. So our study area is here. So the sea level at the Messinian was almost here. So we know that from some seismic data that we have small, not very thick, but we have evaporitic layers in our basin. So we had some evaporation and probably some brines here in this area. So once it went up again, this system could continue. So it's 6 million years ago. It could continue for a certain time, but in the meantime, it's possible that other kind of circulations and maybe more similar to the normal seafloor hydrothermal circulation was put in place. So here to show that our really minimum heat flow was really exactly there where we have such a thin evaporitic layer there. So it's maybe a coincidence, but it's quite interesting. So to finish, for the moment we don't have a real proof, but we have this very large heat flow low here, and then we have nearby these spots where here we have two very high heat flow measurements, but with some low heat flow around it, and here we have this area where we have more high heat flow measurements here. So we are wondering if these systems could be a hydrothermal circulation, so if this is a recharge linked to a discharge here, or if this system maybe is induced by a brine reflux that started during the Messinian crisis. So we want to go back there with the submarines, and because for the moment we only did measurements from the ship, and we don't have very detailed, we even don't have any observations of the high heat flow spots, so any visual or detailed observations. So thanks.
Thank you very much.